Hello and welcome. Thank you so much for joining me. It is great to have everyone here on this lovely evening. Today, I have with me a very special guest. I have Matt, almost a doctor. Hello, Matt.
Hello, how are you going?
I'm fine. How are you?
I am enjoying having a day where I can work from home for a change, but I'm very, very excited to chat about this because even though it's not 100% my field, astronomy, I am in optics, and I mean, who doesn't like astronomy?
Okay, very good. Cosmic Kyle is here. Hello, Cosmic Kyle. It's great to have you. I met Kyle at the Better Conference in Fort Wayne just last month, so that was pretty cool. Um, So let's start out with talking a little bit about who you are and what your background is, and then we'll get into what is the James Webb Space Telescope. So go ahead, Matt.
So, okay, for those who haven't seen me on this channel before, because I've only been here a couple of times, as my kind of handle suggests, oh, this side, sorry, camera's inverted. I am doing a PhD in physics, hence the almost a doctor part. And I'm in optics. I'm working in environmental monitoring, but my expertise is basically how light and matter interacts. How do we know what a molecule looks like? How do we know what elements slash molecules are actually present in a sample? And so that light, that optics side is actually very, very closely related to astronomy, because a lot of astronomy is you take some colors of the electromagnetic spectrum, and by colors I'm not just referring to the ones we can see, but all of them. You can go from gamma rays and x-rays all the way up to far radio waves. If you like the Parkes telescope, that's the famous one that received the moon landings, and I've been fortunate enough to visit that one. So kind of my background is both physics and chemistry, and that's where I come from. And so hopefully today I can actually explain how the James Webb Telescope actually works, as well as what we're looking at. Because as we'll get to a bit later, what you're looking at, the colors you see here, are not real. This is not actually what it looks like. It's something a bit different, but this does have a lot of meaning. And so I'll get to what that meaning is in a bit.
Okay.
Hopefully.
Tell us a little bit about the telescope, when it was launched, and what it is.
Okay, so this telescope was only launched this year. It went up recently. There was quite a few delays to its launch because, amongst other things, they dropped it. They
Oh,
actually
wow.
broke it because the drops. Yeah, they I believe they did break it by dropping a bit of it. This telescope, in and of itself, before we even get to the images it's taken, is an amazing feat of engineering. It has to operate at lower than minus 200 degrees Celsius. So we're looking incredibly cold. They're temperatures you will not ever see on Earth. Even if you go to the freezing depths of Antarctica, you will not get these temperatures. And so it actually has to avoid the heat from the sun. So if you look at it, you have the actual telescope part, the lens, which is what looks like the honeycomb with the little hexagonal plates, which we'll get to. But then you also notice what looks like foil sheeting, and there's several layers of it. And that's the heat shield. And it's designed to block out all of the heat from the sun because it needs to operate really, really, really cold. Also, the detectors have to operate even colder than the rest of the telescope. So they actually made a weird kind of, it's like a refrigerator that uses sound to separate hot and cold. It's, without diagrams, very, very complicated to get into. So I might leave that one for another time or further questions if people have them. But it has to operate cold. It's got several layers of heat shielding to try and disperse the heat before it reaches the plates. If it gets too hot, you won't get any images. So this is designed to get in, because it's actually not a visible wavelength telescope. It's not actually looking up at the sky and seeing what we do. It's looking for infrared wavelengths. So they're a bit longer in wavelengths. So you want it to be cold because for that reason, plus actually how some of the parts operate. So and it's looking at things that are incredibly dark. It receives about 1 photon per second when it's looking at its images. To give an idea, if you look up at the sky on a particularly good night, find the brightest star, and I heard one of the cosmologists, or one of the experts who actually was building the telescope from NASA talking, and he said that you're getting about 1 million photons per second from that star alone. And I imagine Dog is correct on that one. And there's another way they shield it, but I'll get to actually where it is in orbit. That comes a bit later.
That was my
So
next question. Yeah.
Yeah, so it's actually looking for things that are so incredibly dark, but it's been put in a place that makes that easier. Still get to that in a moment, which is also why if you look at the mirrors, they're not silver. They're not that kind of clean mirror-like one. They look yellow. They're beryllium mirrors. Beryllium is more brittle than metals, so it is more prone to snapping, but it will deform. Well, like you can bend, like you can push on it more without it deforming, which is why they needed it. They needed the mirrors to hold their shape. And then there's a whole bunch of motors. So every one of those little honeycomb sections, I think they're at least 0.7 meters across. They could actually be a bit bigger. I have to check. So they, like, when you put them next to them, like they're not much bigger than I am. Like when you look at the whole mirror, like each little panel, and there's a whole grid of them, but each one of them can not only move as an independent one, but they can actually bend the actual shape of each of them, so they can refocus them all. And that was one of the first things it did once it deployed, was they moved all the mirrors to make sure they're all focused on the detector, which is, I think, it's in the order of hundreds of millions of dollars for the single detector that, it's actually probably an array of detectors that's sitting there. So this whole thing is really, really fancy. It's 62% lighter than Hubble, but Hubble has a smaller lens. And this is one of the benefits of James Webb, that when you're looking at telescopes, the bigger the lens, the better the resolution you get. And that's a limitation based on physics. You need to be able to resolve pixels apart. And you can actually talk about pixel size. I remember we had a physics assignment back in when I was second year physics, where it was all the, you've probably heard some of the myths about spy satellites in the Cold War being able to read newspapers over someone's shoulder. We actually got asked, a more basic version of that is, could you identify someone's space from lower, or someone's face from low Earth orbit? So we did all the calculations, and it's not really possible. The size of the lens would be, Hubble's about 2 meters roughly, and this you would need more than 6 meters, and that difference in diameter is quite significant. However, James Webb is about closer to that 6 meters, but of course it's not designed to look at Earth.
How big is the entire telescope?
It's a couple of, I think it's about more than a story tall. It's about a story and a half. The actual mirror itself, I believe, is roughly, so the grid pattern is about somewhat 6 meters in diameter, if I remember correctly. The heat shielding is bigger than the mirror, but it was all designed to fold over. So it actually, despite being bigger than Hubble, it's actually lighter. And that was one of the biggest things they worked on at NASA. Is one of the reasons so hard, is that it had to basically fold over and compact on itself. And so it had to actually fold out, and it took several days for it to deploy. It wasn't just like in the movies where you see like the shields come out in sci-fi, and then it's a big array, or they have the solar sails that deploy in a matter of seconds. This one here took quite a long time to unfold. There's about 300 points of failure for the heat shielding alone. Plus, as I mentioned, they had to put all of the motors to be able to correct the lenses, because they learnt from Hubble that they needed to have a way to correct it. Because Hubble, when they deployed it, they realized they'd put the wrong optics in. They'd accidentally ground the main lens too flat. So everything coming in was blurry. But because Hubble is in a much closer orbit, they're able to get people up and actually replace it. They actually have to physically go up and fix it. And then they could do a few calculations post as well. But James Webb is too far away for that, where it is now. And that was the other one I'll get to, is where they have it.
This is not a serious question, so you are welcome to treat it with the humor that it deserves.
I mean, you never know. Maybe it is. Maybe NASA is lying to us. Maybe where's my shill money? I'm still waiting for that. If we're getting shill money, why haven't I got it? I'm here. I'm talking about it.
Now,
There we go.
okay, what was the process? Was this launched into space? Was it taken to the space station and deployed, or how did the space telescope get to be where it is now, and where is it?
Okay, so it was launched in one go. So if you ever look up videos of how they were making it, you will see them doing it in what looks like a giant warehouse. And you'll
Mm,
see them folding things out. You'll see sometimes the mirrors deployed, sometimes half the mirrors folded around. The whole thing basically folds up like origami. And one of the problems they had was that the engineer described, one of the chief engineers described it as trying to fold a string. If you have a string on a bench and you push it in, it's going to fold differently every time. And so one of their biggest problems was, how do we pack it so that we know exactly how it's going to deploy? Because they needed this to be perfect. I said, if something goes wrong, unlike Hubble, this one's too far away. So they had
mm,
to fold it up so they could launch it in one go. I can't remember the name of the rocket, but it was one of the recent NASA launches. It wasn't a commercial one. It was a NASA launch. Although I have to double check the name because that's one area I still need to look at. So it went up in one go. They launched it and it kind of deployed. And as it was moving from Earth to the point where it is now, I said I will get to that in a moment, over the course of many days, it slowly deployed. So it wasn't in one go. And where it is now is they launched it close to the equator, because most launches are done there because that's where the Earth's spin is the fastest, so you get a bit more of a boost. But it's launched basically and is sitting in Earth's shadow from the sun. Because as I mentioned, they want to avoid heat. It needs to be cold. So any kind of help they can get from the Earth is good. And that's where I need to introduce a tiny bit of maths, but I won't go into any of the actual formulas or anything. I'm not here to give people maths homework. It's sitting at what's known as a Lagrange point. So when you have orbits, things move all the time. If you look up at the sky, you can see the stars moving because as we're rotating around. But if you look at like other planets, they'll come in and out of our vision all the time because they're at different orbits. They have different speeds to us. Orbital velocities are all different. So things move. It's all very, very dynamic. But they needed to find somewhere where that wasn't the case. This needs to be aimed at the same spot in the sky, yet it needs to stay in Earth's shadow. And so a Lagrange point is where in an orbit, there are stable parts of it. It's just mathematical, and it's where if you put something in that spot, it will not move. And
mm,
there's, from memory, about at least 4 or 5 of them. One of them is the very kind of opposite side of our orbit. So it'd be if you just draw a line out through the sun and then on the far side, you're thinking about the actual orbit. Then there are 2 that sit in the same orbital path. So here's Earth, here's the sun, like out here, and then kind of out here. So as we go around, they kind of follow us. And there's a second massive kind of like asteroid belt around Jupiter, because Jupiter is so big, it's got all these asteroids sitting in those Lagrange points, and they just stay there and they orbit kind of in the same ring as Jupiter. There's one that also occurs between us and the sun. So you can put one, it's a bit closer to us than the sun, but it can sit there. And so as we go around the sun, it's going to sit in the middle and go with us. So from our point of view, it's always going to, but of course we couldn't put it there. So the last one is where it is, and that is behind the Earth. If you go the right distance out, there is another Lagrange point where if you get it perfect, as the Earth goes around the sun, it will move the same speed. Now, it's not in the exact same spot. It kind of goes around in a circle, but it's going around in a circle within that shadow of the Earth. So it stays pretty much relative to the rest of the night sky in the same place compared to us, which, as I said, that's the key thing they needed. They needed that shadow. They needed it to be in the same spot because they're looking for very dark objects. And I will get to the image behind me because
right. First, I have a question.
you can't
here
see
from
this with
Kyle.
your own eyes.
Yeah.
Oh, sorry.
Kyle asks, is it within the JWST power to directly image an exoplanet?
I believe it is, yes. I think that was, I remember that being one of the talking points. I believe it was last year, even the year before, when they were thinking about launching the satellite. They were talking about its ability to image exoplanets. I would have to look into it because as of yet, it hasn't, I don't believe it's spotted any. They did fire it at Jupiter, but but James Webb, you just like Hubble, you couldn't turn it around and look at Earth. It is it is designed to look at things a lot darker than that. You would actually, just like Hubble, you would ruin it if you tried to look at something as bright as the Earth. So it is designed to look for very, very dim objects, which exoplanets are. I don't think we're going to find any in the image behind me. That it's just everything there is too far away. But we'll get to that. But they did an amazing image of Jupiter with this, and in that image you can see Jupiter's rings, because Jupiter, like basically Jupiter onwards, except for Pluto, all the other well, I mean Pluto's not a planet, but all the other major bodies in our solar system have rings. Jupiter, Saturn, I mean Saturn obviously, but Neptune, Uranus, they all have rings around them. They're just very, very faded because the rings don't last as long as the planets. So Saturn's rings are only a few 100 million years old, as opposed to the 4 billion years old that our solar system is. But in this image, you can still see the remnants of them. They're there. They're just really, really dim. And one of the things I find is kind of sad that we humans didn't evolve earlier is that Jupiter in the early solar system, thanks, Don, a dog. But yeah, I even think James Webb would still have trouble spotting his brain. I know it can spot dim objects. We're looking at a photo in a second, but yeah, it's too dim. Is that Jupiter would have had a more impressive ring system once upon a time than Saturn did. If we could go back in history, it would have bigger rings. And one of my favorite images from Cassini, which was the base of the orbiter around Saturn that took all those amazing photos of both Saturn, its rings, and its moon system. It was basically the second version of the pale blue dot. I've used as a background in some of these. I'll bring it up a bit later if I have a chance to change the background. Was from Cassini. And you can see Earth in the background. And it's just, it's just brilliant. But yeah, I can't imagine what those rings would have looked like. But yeah, you can see it with James Webb. Which also gets to the last point, as I mentioned. James Webb is not a visible light telescope. It's an infrared telescope. It's not looking at colors we can see. So when you see the images like the ones behind me, that is not what it actually looks like. They're false color images. So it's actually capturing infrared light, and then they're converting it into visible wavelengths to make an image that we can interpret. It's really, really common in astronomy. One of the things everyone thinks of is you telescope, you put it up with a glass lens, and you just look at something. That does still happen. There are visible telescopes, but most telescopes that I've seen, the bigger ones, don't use glass lenses. They use mirrors. You actually have a giant parabolic mirror, so a nice, like a bowl that puts it in a bit like a visible telescope dish, like a shiny satellite dish that you might see on a roof, but a very big version. One that if you dropped a spanner, because some of them are several stories tall, and I've had the lovely opportunity to visit one of the ones in Australia on the visible light observatories we've got. You'd probably get fired, because if that hit this, like, they're polished by basically putting them in a vacuum chamber with vaporized aluminium. So they actually use a gas layer of aluminium to coat them, because they need them to be that smooth. And most telescopes tend to operate that way now. And James Webb is another example. It's got hexagonal plates. That's not a new idea, but making them work for James Webb was a whole engineering feat on its own. I've already mentioned how they can move them. But that's why them being gold isn't a problem. They look gold, but they don't to the infrared wavelengths. We know what certain wavelengths will be when they hit that detector, so we can measure it, which is why you'll also see some photos, if you go looking for them, of the exact same image, but they look very different because they change the wavelength. Because one of the benefits with infrared is that you can actually see through a lot of dust and debris. And so it's not quite thermal imaging. That it's known as the near infrared, and so it's much closer to our red end of the visible spectrum because you go from blue to red. Red is lower energy. And that's another thing that will come in useful for these images is that as time goes on, things get red shifted, but I'll spend more time on that.
Mark Caesar asks, is it possible to get a filter that allows you to see infrared images with a home telescope?
I definitely know that even things like infrared film has been around for a while. So you could see some things. Whether you could do it for useful wavelengths, that's a different question. Some cameras, even security cameras and webcams, can actually see into the near infrared just above kind of 700. You won't get thermal imaging out of them, although these aren't thermal either from memory. I'm not sure if you can do it with a filter. It should be possible because if you're going down in energy, because infrared is lower energy than visible light, that's generally easier to do because you just capture it, lose a bit of the energy and release it again. Going up in energy is a bit harder. That's where you need proper ones. I'm not sure you couldn't get an image like this with a filter. You'd probably need much more sophisticated stuff, but you'd probably get an image. But I'd have to look into it. It's a good question.
Now, let me make sure I'm understanding this correctly. So, the images that we get back from the telescope are images of infrared pictures, and then the scientists that collect the images, they take them and they I don't know what the process is, but basically they turn them from what we would expect to see from an infrared color to what it would be in an actual color if it wasn't an infrared light being measured. Is that correct?
It's a bit like if you look at a thermal camera. You know how
Mhm.
the thermal camera you can actually see kind of red and blue, and it's not really that they're trying to engineer it to be what it would look like if it was invisible, because that's a bit hard to say. It's like, what would thermal imaging look like if it was in the visible, but they're already colors we can't see. It's more of just taking in wavelengths we can't see and then just representing them in a way that we can.
Mhm.
So
Okay. Okay.
it's more of a process that's done quite automatically. The actual science, the part where all the study comes into it, is when they look at exactly what wavelengths are coming back. And this is where my
Mm.
area is very useful.
Okay.
Light and matter have very, very precise interactions. If you have some energy difference in a molecule, some energy difference anywhere, you can exploit it. And what I mean by that is actually quite broad. It can be moving electrons around. It can be making molecules shake. It can be electrons moving the electrons in elements. So you can have molecules, you can have elements. And so I do need to look a bit more into exactly what James Webb's capabilities are, but in a lot of astronomy, infrared can be used to try and pick up what elements you might have present. But as I said, it also allows you to look past dust, because certain ones won't show up at certain colors. Because if you look out the window right now, your window is clear. To us, it does not absorb visible light, but eventually it will start to absorb, say, ultraviolet. So you can get a bit of protection. Sunglasses are like safety glasses, and sunglasses are another good example of where things will. I mean, sunglasses are tinted, so probably safety glasses, the better one, or the plastic safety glasses. They'll protect you against UV light to varying degrees depending on their quality and exactly what they're designed for. They're clear to us, but they're not clear in other wavelengths. And that happens with a lot of material. Not everything is the color we see it. There are a lot more wavelengths, and it becomes really complicated. But that interaction tells us a lot. And one of the ones that is so amazing about James Webb and actually tells us how old some of all of these dots and smears and everything that we'll get to are is how red they are, which is another reason why infrared is really useful, is that they're so old that a lot of the wavelengths over time have been stretched to become longer. So it's actually, even if once upon a time they were visible, they're not anymore. And of course, as I said, you can actually look through things. One of the other images I want to come to is amazing for that. It's the problem is it's a really complicated one. It's like, how much do I explain versus how much do I just leave to?
Yeah, we could go on probably for 20 hours before we completely emptied your brain.
Oh, I've spent the last few years looking at building gas detectors that involves infrared wavelengths for methane.
Mm-hmm.
For one chemical, about how do we know how much of it there is right here? How long how long have you got in terms of explaining all of it? But these images, they're not visible ones. So it's a bit like when you see false color images when you look at, like, say, a really good one is if you want to look at like ocean mapping depths, where they use colors to depict depth. The
Mm-hmm.
colors are not depth, but they're useful as a way to show the depth. And this is another way of doing it. They're wavelengths of light we can't see, but it's just a way to show it. This is the light that's coming in. They've just obviously put it at a wavelength we can see. They've just changed the color.
So how far away are we seeing with this telescope?
Distance is a hard one, but
Okay.
time, I can explain this one a little easier.
Okay.
Let me just see if I can move a bit to the side with this one, or if you want to, I know
I can bring up
the
one of
link.
the images as a share screen.
Actually, yes. If you can see if you can find this one from the NASA link I sent you, I'll explain it a bit better.
Okay.
See how it's curved? It looks like a bowl. That's what it actually looks like. That's not the lens of the telescope. That's not distortion from anything we've done. That's what it looks like in space. And that's from gravitational lensing. So I've got an eyelash in my eye. The gravity bends space-time. And as light travels through, you can think of it like a trampoline surface. If there's nothing on it, if it's empty, it's flat. There we go. Yes. There's also, both the links I sent I think have this image. The other one is the NASA one. It might be a little clearer. And you won't get cookies. The NASA one, I think, is probably the easier one to use. But if we look at see that circular pattern, that smearing, that's actually from gravitational lensing. And so coming back to the analogy of like a trampoline surface, space is like that trampoline. If I start to put mass in there, so objects that weigh something, just like putting a heavy ball on a trampoline surface, it will bend inwards. It'll sink into where it is. And so as you everything wants to travel in a straight line, but as soon as you have mass, that'll deform it and things will bend. Think of an orbit as basically going around, kind of spinning in one of those dips. But this affects everything.
Now this picture is different.
Yes. Just go through the little blue tabs at the top. They have the different images. I hope this one has that other one. I know these. I know most of these. Oh, okay. Maybe it isn't. Oh, okay. Sorry. Maybe the other one is the one with it.
Oh, there.
Oh, yeah. No, that's it. That's it. This
go.
is one of the first images. Just scroll down for a bit. I like the center bit. Just like when you have objects falling into a gravitational well, light will do the same thing. You can bend light around objects. And a lens can be round. You can actually make a spherical lens. Most lenses are kind of convex, concave, just like glasses lens are. But gravity does that. And so when you have really, really heavy, really dense objects, like there is a massive galaxy in the middle of this that's doing that, the light gets bent around it. And what is really useful in astronomy is it allows us to see further. It's like a telescope made of galaxy. And yes, it distorts the images, but those smears, those tiny red smears that you see in that circular pattern, are some of the oldest objects in the universe. Because for the early universe, there was a time where there was no light because the universe was too hot and too dense for light to escape. And you don't actually have anything you can see at that point. The universe to us looks black. But the moments where it first started to cool down is where you get the cosmic microwave background radiation. And so over time, that's been stretched out to the microwaves. That's one way we can tell how old the universe is. And the other one is when you started to get galaxies to form in that early universe. There are a couple of tiny, tiny red dots in there that are not even smears. They look like stars. Those are galaxies that are some of the earliest to form. And I believe some of them are more than 13 billion years old. The galaxies are about 700 million years old in terms of the universe, which I just cannot think of an analogy to describe how old that is. Like our human brains just didn't evolve to comprehend that. It's just impressive. Some of these galaxies probably don't exist anymore. We're looking back in time. The further into the center we look, the closer to those circular spheres, the older we're going, more or less. It's a look back in time, rather. And so thinking of distance is a bit harder because the universe is expanding at an accelerating rate. So where we're seeing these objects is not where they sit anymore. And so that's also comes to the next bit about how we actually know they're that old. As the universe expands, the space between molecules, between like the actual space within space, expands. It gets bigger. And when we're thinking about wavelengths of light, if I start stretching space out, I will stretch the wavelength. It will get longer and it will get redder. So when we talk about redder in science, redder or redshift, people have heard Doppler shift before. I'm not thinking, we're not just thinking about visible going from, say, blue to red. We're just stretching wavelengths longer. And of course, we talk about it redder because, yes, if you are invisible, it goes towards longer, towards what we would see as redder wavelengths. But it keeps going. And so there's another number that I've seen a bit and is quite common for it, and that's known as the Z number, which is how redshifted they are. About half of the universe has a redshift less than 1. About 90, only 3% of the universe has a redshift above 10. And we're looking at a lot of objects that are some of these objects are about 15. It's not a linear scale. I can retweet something I saw from one of my former professors who's amazing on this. He put up a little graphic for the numbers. But over time, as the universe gets stretched, the colors get stretched. So the older they are, the more redshifted they'll be, the redder they'll appear to our detectors. And that's why a lot of those smears, the faraway ones that we're looking through our gravitational lens at, our dense galaxy, are quite red. They're longer wavelengths. I know this is in infrared, but it is roughly matched to the visible to try and give us an idea of what's going on. And so we're looking back at time at some of the earliest galaxies to form in the universe. This is the beginning of the universe as we know it. The beginning of stellar formation, the beginning of all of the materials that basically eventually in the tiny fraction of the spiral arm of the Milky Way galaxy gave rise to this solar system, and then recently, almost in the last second in a cosmic sense, gave rise to us.
Do you think it's possible with this telescope, or might be at some time, possible to find where the singularity began?
We can trace back and figure out what the center of the universe is. That would be possible. And I believe the universe has been mapped. I actually have seen an image where a paper went through and pointed out where on the universe we are. We're in a tiny branch off to the side. And then in that tiny spot, we're in the Milky Way. We're on the tiny spiral arm of it. We're in the middle of nowhere from a universe point of view. The problem is that, as I mentioned, the universe for a while was dark. The actual singularity, and that there's another issue that we're about to get to with that, is that the universe didn't have any light. There wasn't anything to see. So unfortunately, I don't think it's going to be physically possible to directly see that moment. You just can't do it. We could definitely trace it back and get a better idea. And this is what this is doing, is we're trying to go back in time. We're trying to see how the universe developed. Because if you can trace out, it's like if you have an explosion, you see all the bits of debris flying out. You may not see the initial point which that explosion occurred, but if you have a good enough map of where of those parts have been flying, you can kind of do a reverse, and then you can keep tracking it back. You mathematically, scientifically determine where all they sat and what did that object look like. But one of the other problems is that whilst mathematically we're talking about a singularity, quantum mechanics doesn't really like singularities.
Mm,
And so the idea of time at t equals 0 doesn't make sense.
hmm.
Almost time
That
becomes infinite, and it just our current understanding is not sufficient to answer all those questions. Now, that is not to say that we have no idea what's going on. It's that we don't really have a way to test the more nuanced theories. So the bouncing cosmos is one idea if people want to look into it. If I started explaining it now, I mean, one, I'd need to look more into it because it's still fairly new to me, but it's amazingly complex. One of my favorite quotes from one of my professors, who was one of the ones I mentioned earlier. I'm just not name dropping because they're not here. He said, and I like this quote, and I do agree with it from what I've seen. He said, most cosmologists don't think there was a time at which the universe had no yesterday. In other words, he's saying that the universe didn't have a beginning in the traditional sense of it because time does not make sense.
mhm.
And that's one of the things that it's really hard to explain because there is no proper explanation for it.
I had a very difficult time with it as well, until I listened to Rationality Rules explaining, how the time before time in the beginning of the universe is incoherent, and listening to him explain it made a lot of sense to me.
Yeah, and I'll have to go see what he has to say on it. But from a physics point of view, most our understanding at the moment is that our understanding of time is insufficient to describe it. What we think of as kind of temporal causes and cause and effect, time flowing on second by second, hour by hour. Dog's at it again.
I've been holding two serious questions for you for when you've got a break. Is this a good time for them?
We can go for it. I just want to finish the yes, but when you deal with things on a quantum scale, when you get to the sorts of sizes that you'd be talking about with singularity, events can cause themselves, or the thing that causes an event can actually temporarily occur afterwards. Because when you're dealing with quantum mechanics, there is enough of an overlap in waveforms. You might have heard that in quantum mechanics, everything's a wave and things can be in two places at once. That's not entirely accurate. It's not that it's in two places at once. It's that it's in a waveform. It's in a lot of places at once. It's in an area. It's in a cloud at once. You can map it as a wave thing. It's actually, when you look at what electron orbitals, because that's, chemistry background I look at, you'll look at, maybe a sphere or this weird figure of 8, not these little dots flying around. You don't actually, generally speaking, they're not a dot. They're only a dot at the moment you observe them, but as soon as you observe them, they go back to being a cloud. You don't know where they are. And so what they do is they say, with 80% chance it's in here. And with quantum mechanics, that's the same thing. But it also can move into time-wise as well, where the probabilities overlap. So you can have events causing each other in this weird chain that does not make sense to us. And we don't yet have a sufficient understanding of the early universe to be able to say exactly how it went, because it's physics and it's maths that we can't study. It's a scale that we don't have access to. That's not to say we don't have any idea. As I said, there's a lot of work going into it. People spend their careers working on this. It's not that, we haven't figured it out, so scientists have no idea, and then there's a eureka moment. There is no eureka moments in science. The most you're going to get is, the equipment's not working the way I thought it was. Yeah, that's interesting. Let me spend years trying to figure out what's going on. It's a slow process, but it's steady. Yeah, Ted is right. That gravitational lensing is basically we're using a galaxy as a telescope, just like the lens in your glasses. And so I think there's one just above my head, and
That
there's
big
another one
white
a little
dot?
down there. I'll get. Oh, I'll explain the dot in a second. But there's a couple that look like these little smears of like little dots. One of them got, I think it's about here, so up high my head, got nicknamed a pearl necklace because it looks like a pearl necklace, but it's just a galaxy that's kind of been bent a bit. There's a couple of dots. I heard about some of my physics friends were talking about pregnant snake, which is basically a stretched out stellar nursery with a bunch of stars in it.
Does that help better?
Yeah, so see, some of them there, it's a bit hard at this distance, but a few of them, yeah, there's one that got called the pearl necklace, but they're generally flat. They're just bent because of the way the lensing works. But that bright star in the middle of it, I don't even know if it's 100% a star. That effect where you've got the lines coming out of it is actually an artifact of the of optics. That's not what the star looks like. It's actually diffraction through, I believe it's just dust in space where you've hit dots and the pattern is spread out. That it is a diffraction pattern for sure. Diffraction is just when light passes through any opening or a particle or an object and it kind of gets bent and you end up with all these patterns forming. It's basically how light develops over space. You can do it with anything that's a wave. And the double slit experiment's the go-to if you want to look into the basics of that. But it works here too. And one of my favorite ones is you can measure the width of your own hair. If you get a single strand of it and you shine a laser through it, you'll actually notice the laser hits the hair and then you get a spreading out. You get a bunch of dots on the wall. And based on their distance, you can tell how wide your hair is. It's kind of what's going on here, more or less. It's hitting objects and spreading out. But it does so in really, really cool patterns. My favorite one is from the chemistry building where I teach. They've got mesh blinds that come down, but they're not fully opaque. You can kind of see through them. And you can see the traffic lights. And you can actually see the diffraction pattern in the traffic lights. And as they change color, because different wavelengths will spread out to different degrees, hence how you get rainbows. If you shine a white light through a prism, you get a rainbow because the different wavelengths will spread to different degrees. You can actually see it happen through this mesh because you've got little holes that act like little mini apertures. So you see the traffic light spread out, and then as it changes color, the degree of separation moves. And I just had a really nerdy moment where I sat there for a good few minutes watching the traffic lights. Just because it's like, hey, look, I can verify that what I do is accurate. Despite how many other times I've done it through lenses.
And then the guy behind you gets upset.
Well, I mean, I was just teaching high school students, and I had a bunch of
So you weren't
scientists
sitting
behind me.
So
at a light. They came over and had a look. That was they were like, oh, that's cool. And they came over and they wanted to look. I think I stayed there a bit longer than they did, but optics is my thing. It's a difficult one though to explain without lots of diagrams. It's a very, pun intended, very visual learning process.
Okay, I've been holding a couple of questions for some time now. So
yes, I've been talking way too much.
That's okay. Okay, first question. Will this telescope reveal new portions of space previously hidden, potentially deeper than the current cosmic horizon?
One of the ones to go to for that, Cosmic Kyle, is look up the comparisons of some of the images, such as the one behind me, with the ones Hubble took. The main benefit to James Webb is that because it's a much bigger lens, looking further, as I said, we do get to some physical limits, but we can look at things with a much higher resolution. The image behind me, this entire image, those galaxies there, some of them are bigger than the Milky Way. Some of them are more than 13 billion years old. They're like 98% of the universe almost, like in terms of time. They're in their first few percent, some of them. A lot of these don't exist anymore. They're just that old. The entire galaxy could be gone. We don't know because, unfortunately, light and information doesn't travel far. Well, nothing travels faster than the speed of light, including information. We can't, unless we invent warp drives, which is theoretically possible, but that's a discussion for another day. Is that what it does is it allows us to see things in better resolution. So we can pick up more detail in objects. The diameter of a lens is very important. So Hubble, Hubble's still very powerful. Don't get me wrong. And it's, again, they're looking at slightly different things. The wavelengths are different, which allows us to look at different things. But if you compare the images from Hubble to the images from James Webb, you can see such an increase in resolution. This entire image, to give you an idea of how much of the night sky we're actually looking at, and this is basically looking back to as close to probably the beginning of the universe as we've ever seen so far, is if you picked up a grain of sand and held it at arm's length. That's how much of the night sky we're looking at. It's tiny, tiny fraction. And that is why we needed that to put this in a dark spot. We needed those cold temperatures, and we needed to shield it from light that we didn't want, because it's looking at 1 photon per second. So when you're in a night sky looking at a bright star, it's about a million photons a second.
Okay. The other question that I starred and kept is not a technical question, but it's a question that people like me tend to ask. That is, this might be stupid, but space universe is expanding at an accelerating rate. What is it expanding into?
That is actually a very good question, and it's a difficult one to answer, but one of the things is that it's the fact that actually space itself is expanding. It's not just like Earth is moving further away at an accelerated rate from the rest of the universe. I mean, it is, but it's also the fact that the space between objects in space is expanding. The space between atoms, the space between molecules is expanding. You're not going to notice it if things are not even. So for a human, for Earth, the atoms and everything are quite, there's no nice, neat pattern to it because there's disruption. I mean, look, we're human. We're not. Our whole makeup is not some nice, neat structure, whereas most of space is fairly empty. So it's more or less that nice pattern that you can get. But when you're dealing with that, it is actually the space itself that's expanding. And that's one of the things that been stretching those wavelengths. And that is how we know that these things are more than 13 billion years old, because I know with your channel, you might get some people who want to come in and tell you it's young. It's not that we're looking, that these things have just traveled. These photons have spent more than 13 billion years traveling, and of all the places to land, they happen to hit the James Webb Telescope after an immense amount of time that we just can't comprehend. It's also that as they've traveled, the actual space between the waves has been pulled. It's been stretched. And so the reason that they're as redshifted as they are has as much to do with time as anything else. It's taken time to stretch them. It's not that just because they're far away that they get stretched. One of the relativity ways, if you're just thinking more special relativity or even general relativity, actually, no, this is general relativity to think about, is that also because we're moving faster and faster away from things, it takes longer for the wavelengths to reach it, so it looks longer as well. But the space expanding is probably the better one to go to. It's that they've needed 13 billion years to get that red. It's so because I know you do get have a few things where you discuss young Earthers. For this to be designed in whatever they want to suggest, that is very deceptive. It's not that the light was made coming to us so we can see things further away. It is as though for every detectable purpose, for everything we can look at, it appears as though that light not only was close enough to reach us, but that it's actually been traveling for that time. It has been traveling for billions of years, even if we're talking about some of these younger galaxies in this image. And that is a brilliant question too, because our Milky Way galaxy is actually going to collide with the Andromeda galaxy. We've still got it. I think it's still like a trillion years away, and there are some brilliant simulations of what's going to happen. If, let's say, you froze Earth in time and you accelerated us to that point, the moment of collision, we wouldn't really notice.
Oh, really?
Because space is so spread out, because there's so much distance between our solar system and the nearest stellar bodies, we wouldn't, from a ability to live point of view, notice. I mean, it's going to be so far in the future that our planet will not be here, and if it is, it's after our sun went red giant and basically fried us to a crisp with radiation before collapsing to a cold white dwarf. Earth's not going to be habitable by then, and of course, I don't think any of us will be around because, again, we're talking about 1 trillion years. And our sun, I think we got about another billion years before Earth becomes uninhabitable. And about, I think, another 4 billion years before the sun will go. But it'll get too violent. It'll be giving off too much radiation in about 1 billion years. But if we did manage to see it, we would collide. And if you look at simulations, I've seen them, they kind of mix and they swirl. It's like clouds of dust moving with each other. You don't get, and yes, the supermassive black holes and the really dense centers are definitely going to notice. That's where the most activity will occur. But yeah, galaxies can collide. They will. Stars collide all the time. The LIGO detection was 2 black holes. The first one was 2 black holes. We had 2 neutron stars. I remember going to a talk by one of the now professors at the uni who did a brilliant talk on that, and that actually a lot of the material doesn't just come from the supernova, so it's like a star kind of going nova at the end of its life. By the way, our star won't do that. It won't explode. It's too small. You need to be about 10 times the size of our sun to go supernova. Some of them don't go supernova. They just collapse into a black hole. It fails. And we learned that because all our simulations kept failing. That's a weird way we found out because we kept trying to simulate it, and half the simulations, or like a whole bunch of simulations, didn't work. They just ended up with nothing, just a black hole. And they're like, okay, what are we doing wrong? Until someone went, what if the simulation's right? What if actually this happens? What if they do fail? And so they went looking, and yeah, they actually saw a star that just blinked out. And they were looking for the exact amount of time that you would expect based on how much of the sky they were surveying before you saw that occur. So it was quite cool. But yeah, a lot of this is kind of the simulations. If you want to go back, so I know that's going to a little earlier questions, that you will do simulations for where you trace back and you see if you run these simulations, do you get to where we are now? If you do, that's a really good indication that the physics in the simulation is correct. As I said, it's kind of that mapping those paths. If you can predict where everything got to, then your model is probably fairly accurate. But yeah, the galaxies colliding is a cool one because we could probably get a better idea of what was happening in that regard too with images like this.
Now, one thing that we talked about a little bit before the show started, and you mentioned you were going to start with this, and then we kind of ended up skipping over it. And we didn't get to it. Was that you work with people of different faiths, and faith and religion really doesn't get to be an interfering factor in your work. Talk about that a little bit.
So yeah, because I want to, because I know particularly your channel, there'll be probably a few people watching, and I'm sure we could all think of a few people who would try and come into the chat to derail it. We'll, I think, know who we're talking about without names needing to be mentioned, who like to think that, you know, science is somehow against religion, or it's there to rail against spirituality, however you want to understand that term. But I have worked with so many different people of many different beliefs. I have worked with people who are incredibly religious, who could be very spiritual, some of whom are more like me, others who are quite, you know, extremely kind of almost anti-theist. And at no point has that ever got in the way of the science that we have done. I have never set out, and nor has any scientist I've worked with, to try and destroy or to even impact someone's spirituality. I've got friends, and I would call them friends, who I've worked with who are deeply religious, who, for example, one of them thinks that all of the stuff with the fundamental particles and the colliders leads to some spiritual sense of the universe. But up until the point that we can do the science, we're on the exact same page. And to us, it's a fascinating conversation. I've got friends who are deeply religious who think that the universe is finely tuned, which is a weird one because most of them, the actual fine tuning, you need an old universe, because those constants is how we know the universe is old. And I've had brilliant discussions with them. And at no point have any of them, particularly the ones that will wear religious imagery around, have ever got in the way of doing good science. I find it a fascinating way. And so if I want to get up here, I want to talk about science. I'm not here to destroy or to ruin anyone's spirituality. If you get some spiritual meaning out of this, go for it. I'm not going to stop you. Only time I have an issue is if you start saying something that's anti-scientific, or you start trying to destroy the hard work of scientists, like all my colleagues, like my friends, like myself, who have put decades of work sometimes. It's not an easy thing to become a scientist. So I want to make that clear. This image does nothing to disprove any sense of kind of theology with this. There are some forms of it that have been well debunked, but I'm talking about the more anti-scientific, very, very fundamentalist ones. And in which case, yes, I will happily discuss against those. But yes, as I mentioned to you before, I wanted to make that clear, because there's no, I've only ever had one person in the nearly 10 years I've been at uni. Well, it's nearly 9 actually at the moment. This is my 9th year at uni. I've only ever had one person ever have a go at me for anything to do with religion. There's one professor, and this is when I was still religious. He'd pulled the sort of, if you're not religious, are you? And the looks he got from everyone else in the room showed that that was the most inappropriate thing he probably could have said. Everybody kind of looked at him in horror, and he had a reputation for not really controlling his mouth all the time. But because the thing is, that's not an issue. The issue is whether you do good science. And it's quite a diverse just array of people that we've got, many of whom I wouldn't just call colleagues, I would call friends. I've got a lot of close friends who have all sorts of different beliefs about the universe, and yet when we talk about science, we talk about it the same way.
Shifting the topic just a bit, I'm curious as to the images that we get from the telescope. Is there like a camera that takes a picture of what the telescope is recording? And how many images do we get per day, or how long does it take?
It's actually more how many days per image.
Okay. So it's a long exposure camera.
We're looking at 1 photon a second. These things are sitting there for a long time. Like Hubble, its deep space ones were 11 days. I don't know the exact time for the one behind me. Some of them, like this one, because they are looking at something so dark, is very, very extended exposures. I will have to double check. I don't have the numbers off the top of my head, so I'm not going to speculate beyond the few items I've said from what I know. But in terms of the detector, is it? If you just go to NASA and look up for a picture of the actual telescope, I can point out which bits would do it. Because if you look at a satellite dish, it's a good analogy to it, you'll notice that you have the actual dish which reflects the radiation. In this case, I mentioned it's infrared, into like a little detector that sits out in front. And that's how James Webb operates. It's got its detector that sits in front of the mirror, and the mirrors all kind of reflect the light back in, they focus it in. All of them had to be calibrated, so they're all moved around to make sure that they're focusing it perfectly into the detector which sits there. So that's one of the more expensive parts of it. One of the most, though, from an engineering point of view, challenging items to make was how they kept it so cool. It's basically got a weird temperature refrigerator thing that uses sound waves to generate cryogenic temperatures. It's about 6 degrees Kelvin, which is about 6 degrees above absolute zero, which is insanely cold. As temperatures that are difficult to get on Earth, let alone a tiny satellite floating so far away that if anything goes wrong with our current technology, we can't get to it to fix it.
Now, is that the launching of the telescope?
No, I think that's because it wasn't aboard SpaceX. I'll have to double check for it. Unfortunately, I don't remember the name. Let's see. So, these are cool. There's a few more images I do want to get to if we have time.
Okay.
Let me see if I can find them. I'll bring them up because there was a few. Images.
Yeah, I'm not finding any images of the
James
telescope
Webb
itself.
Actual. It's a. Here, I've got one in when it's in its lab. This is from... So, let me see if I can... So we've got... so this one here, this is the actual one that we're talking about. So one of those panels there is not a lot smaller than I am in terms of height. When you put them next to a person, because they're quite wide, they look, puts it into perspective, and you can see what looks like foil is actually a weird form of tape that they've actually plastered all sorts of really, really fancy materials on to help shield it, and it all folds out. But yeah, you can see those panels. You can see in the middle, and then held out on the two arms in the middle here is the detector. So they're all the mirrors, and each one of them can bend and twist. So the detector's kind of up the top. Let me stop. Yeah. So that was kind of what I was talking about. So yeah, there's a few out there. Here's one other image I really want to get to. Oh, here we go. Why do alien invade? Oh no.
Oh, you want to see that? Why do alien invaders overwhelmingly have an interest in probing Midwest Americans' bum holes?
No kink shaming here.
Can any of the images get close enough to see the surface of, say, an Earth-like planet? I'm wondering if it's possible to find that maybe there was intelligent life on another planet that went extinct or something.
I have the feeling that's probably not going to be possible. I think
not
to actually get that much detail,
to
actually look, because I'm guessing you're talking about like sort of like artificial, like cities, things that are artificials, structures, etc. I think you'd almost need to get in orbit with. I think the actual diameter of the lens to get that sort of resolution, we're not talking about anything we can currently put into space. It'd just be too big to put on a rocket.
So we still need to invent warp speed technology.
Yes, the other one that it'll probably come first is constructing telescopes in space. So instead of launching them like this, like Hubble, where they're launched and then they deploy in space, we would actually build them bit by bit on Earth and send them one part at a time, so we can actually build very, very big telescopes. There is a really, really cool way to make telescopes where the effective diameter of the lens is actually wider than the Earth, is where you actually have multiple, and you can do it. I don't think you can do it invisible, although I do have to check that one. Whereas you actually do it in radio wavelengths. These are the most common ways, because they have done it on the small scale on Earth, and they are looking at doing it in space with satellites, which would give you an effective diameter just a bit wider than the Earth, where you actually have multiple smaller dishes detecting ones, and if you put them out, then the furthest away they are, you can actually resolve things as though you had a dish that was that whole size, even though the little mini ones spread out. I know that one of the Australian radio observatories that I've been to does that. They had about 16 radio telescopes, and if you put them far enough apart, you can effectively make a telescope where the lens is, in their case, we're talking probably kilometers across. As I said, if you put another telescope on the moon, you would have an effective lens that with a diameter between the Earth and the moon. But that's still in the radio. You're not probably going to see the detail of a planet in terms of looking for life. Our best bet for finding life at this stage is spectroscopy. So that's actually looking for chemical signatures. You're looking, because every molecule or every compound will have very, very unique colors that it absorbs and emits. Some of those colors we can see. If you want to think about certain colored materials, that's easy. If we want to think about, lasers are a different one. So it's more thinking like stained glass is a good one. That's a really easy one. Oxygen has its own unique ones. There was the whole thing about phosphine on Venus, where they were trying to detect that. That was through spectroscopy. Again, not all of this is visible. You're looking at not just moving electrons around. Sometimes it's spinning molecules. It takes very specific amounts to spin very certain types of molecules, which is a bit hard to depict. Some of them bending them, because molecules are not rigid. They'll bend and they'll twist, and if some wavelengths will cause them to vibrate in very specific ways. So every molecule has a unique signature. The word helium comes from the Greek word helios, sun, because helium was first discovered in the sun before it was discovered here, because when they looked at the spectrum of the sun, they saw colored bands that didn't correspond with any element they had actually detected on Earth. And because helium doesn't react, and it's only in a small, so little of it, that they actually detected it through spectroscopy on the sun. So they saw those colored bands, and that's our best bet for spotting life, is having telescopes that can actually detect those colors. And there is a bit of work with some of the people I'm doing that are trying to find ways to remove backgrounds so we can get better images of that. One of the people I interviewed with Jen on her channel once, Tessa Fisher, she was mentioning that her work is actually on not just looking for single colors, but for what array of chemicals you would get. So it's a whole, like, what would you look as a whole? What colors would you get across the entire spectrum to make things easier? So you're looking for it's almost like a barcode scanner, but with light.
Okay,
we see these colors, we know. Yeah.
This question is a little outside your field, and I know it's going to be speculation, but it'd be still interesting to get your opinion on. Do you think that humanity will one day colonize outside of our solar system?
I think we will. I don't know what scale that will be on, but if we don't destroy ourselves first, which is, I think that's unlikely. I think we could do a lot of damage to ourselves first, but actually completely wiping us off, we're generally a little bit too devious to do that. Even if we nuked the entire Earth, unless we actually rip the whole planet apart, which is unlikely, few people would survive. We're going to do a lot of damage. We have a good history of doing that, unfortunately. And I think that's one of humanity's problems, is that one of our curses is that we won't solve a problem until it's become a serious problem. We're good at solving it at that point, but we do let things get a bit too bad before we fix things. And so even just from that, I think we will. I'm not sure it'll be quite the movies about having an interstellar empire that you can go between quickly. It'll be more about getting groups of people away to other places in the universe where you can basically have self-sufficient colonies that will live. I think that's probably the most likely. I mean, look at how fast technology advances. Let's see where we are. It could well do. Maybe not the universe, but we'd definitely take ourselves out. I was watching Love, Death, and Robots, and there's an episode called I think it's The Dawn of the Mini Dead, or The Rise of the Mini Dead, and it's basically like a little funny like zombie apocalypse done with tiny little like claymation figures, and in the end you just basically hear the American president go, "Screw this," and they all hit the launch button, and they just the Earth just and then they really kind of zoom out to the whole cosmos.
I really enjoy Don't Look Up.
I haven't seen it, but I've heard mixed things. I've heard a few people rave about it, and then I've had some people tell me it's a bit trash. And
when I started watching it, I thought, this is really corny, but it had some really big name stars on it, and I've probably watched it for half an hour before I finally figured out, oh, this is satire. This isn't corny, it's satire. Okay, we have another really good serious question. It's also from Dog. He said, are spectrometers accurate on telling us what objects in the universe are made of?
Yes. In terms of, so astronomy in general is a very inaccurate, well, no, not inaccurate, but a very roundabout science compared to the specificity you can get from other things such as thermodynamics. And part of that is just the limitations of the fact that we can't put a star in a lab and we can't get close to them. We're looking at things from a very limited perspective. So when you actually think about what we've achieved from a single point of view in the universe, it's amazing, the technology that we've got. What we've been able to tell from basically been stuck in a tiny little glass test tube in the back end of the universe is pretty cool. But because of that, there are a lot of things in astronomy where you just can't be that precise with. We're getting better, and by precise, I'm talking about relative error bars within science. So not this sort of, oh, we have no idea. No, we've got a good idea, but there are some things in astronomy where if you get in the right order of magnitude, so within a multiple of 10 of the real answer, you've done well. But not in spectroscopy. When we're dealing with this, these signatures, these chemical signatures I'm talking about, the colors that we're talking about, is one of the most precise things you can do. You can use them. You can use where they sit to in some cases predict not predict, but determine pretty much the exact temperature of a star and the exact temperature in different parts of it. Spectroscopy is one of the most accurate things. One of the problems, again, is resolution. We're looking at things often with a huge amount of background noise, and we're looking for tiny signals, particularly like stars are easy because they're bright. Galaxies are easy because they're bright. Exoplanets, looking for life, as I mentioned, those chemical signatures, that was one of the problems with the whole saga with Venus, is that we're looking at what is essentially a paper-thin layer around a giant glowing object with a giant ass spotlight behind it, which is the sun. You're looking for things that are very, very small. But if you can detect those signatures, we can tell. And one of the other really, really cool things about it is that because we know what they look like, we can actually use that to determine redshift. So we can determine how old things are. We can determine where they're moving, how they're moving. One of the projects I got to work on recently was the follow-up to a project. I'm trying to remember what the original project was named. The new one was Hector. I can't say too much about exactly how it works because I've been told not to. But I'm trying to remember the name of the original one, but it was where you could do spectral maps of galaxies. So you can actually get the exact colors across a galaxy. And one of the things that you can do with that is that you can look at the redshift in different parts. So you can actually get the motion of the galaxy as well as what different parts of them are made up of. And of course, you can do that for smaller objects that are closer as well. You do that for stars. So yeah, spectrometers are one of, like spectroscopy is one of the more precise measurements in astronomy. And I'm technically part of an astrophotonics group. We make objects. So my colleagues recently launched a CubeSat. So one of the things was on one of the benches nearby me is now in space, which is I just find it so cool to think about it. It's so yeah. No, you didn't, Knox. Don't worry. We haven't got to the space fairies. Maybe they can help us. Maybe they can aim the telescopes for us. I don't think we know how to speak their language, unfortunately.
Oh, I thought maybe some of the stars were their wands waving.
Yes, that's actually what distorts the galaxies. See the wands? You know how you move all the sparklers through an image and you get those blur curves? That's what it is. The fairies are invisible, but their wands are not. They're the stars that move around.
Okay, Mark Caesar asks, should redshifting be taken into account when measuring spectroscopy?
It actually is. And so one of the things in astronomy is known as the standard candle. And that's where there are certain events. I think they do actually have a better understanding of what they are now. But when I actually did my senior astronomy course, they weren't 100% sure. They have since figured it out. And I got to look into it, exactly what's going on. They were known as, I think, an A1N1 supernova or supernovae. It's not a full supernova. They were events that occurred and we knew exactly how bright they were and how hot they were. So we knew exactly what the black body spectrum looked like. And based on that, the red shifting, as I said, gives you an idea of time, but also distance. So you know how far away they are. So you can actually we know that this is where what the color actually is at the origin source, whatever's caused it, because this goes for more than just these supernovae, although they're the standard candle. If you know how bright they are, then we can look at them and see how far, how dim they are, tells us how far away they are. So you can actually then use that to determine redshifting. So yeah, it 100% is taken into account. And so when they do all the analysis of these galaxies, they will take that redshifting into account. This is something that is actually fairly precise and very, very, very full on, which is why, as I said, it's probably going to take a few months before, like, there is a lot of preliminary items are coming out, but it will take a while before we get that in-depth science research about exactly what we're looking at. And that's one of the things I'm just like, I just want to sit there and I'm so keen. I want to hear what they have to say. And so I've been, I've gone and I've pestered a few of the other professors around who are the astrophysicists, because I said I work close. I get to fortunately work in groups that are somewhat closely tied to them. My area is not in astronomy. I'm looking down and seeing how much damage we're doing to the planet by making methane sing with a laser. But yeah, I've got a lot of friends who look up, and occasionally I like to do the same.
Okay. I'm kind of wondering how long it's going to be before we start seeing pushback from the young earthers.
I'm sure they're already working on it. How long does
Yeah.
it take for them to make videos? I'm waiting for it, and I think it's very sad because, as I said, I can look at this image and get as much awe out of it as any of my religious / spiritual / whatever the other people I work with. I remember some people we think there are different reasons, different origins for the universe, or like in my case, and say, well, we don't know. We've got a pretty good idea now, but the Big Bang doesn't actually describe where the universe comes from. It's not the start of the universe. It's actually what happens after the universe has started, and that's something that gets people. I am sort of around Discord. Sorry to answer that question. I don't have my own server, but I'll be on a few of them. I know I'm on Claire's, because I think I did see Claire earlier. So hello if you're still there, Claire. I'm on some of her servers. I'm also on Twitter too if people want to track me down. As I said, unfortunately, because my PhD's been so busy recently with other teaching things, I haven't had as much time to do this side of things, because I want to finish my thesis at some point, and with COVID I'm a bit behind, so I've got to work on that. But it's but I think that whole young earth kind of tries to push against the science of this, just robs it of so much of the awe that this image inspires. I don't know how to describe it any more than the fact that we're looking 13 billion years in the past.
It's absolutely amazing. And one thing, you described that, and that describes to a T the one thing that had me clinging to Christianity as I lost my faith. Was I was so afraid that I would no longer be able to go outside and enjoy nature, because I would no longer be able to look at it and say, wow, what a wondrous thing that God has made. And it was funny, because the first time that I finally said, okay, I don't believe any of this stuff anymore, I'm an atheist, and I went outside and went for a walk, I went, nature is even more wondrous than I ever thought. Now that I look at this and realize this is all just a natural process, that's even more remarkable than a God making it.
Yeah, 100%. That kind of happened with me. I mean, I've always loved my science. I've always been into it before and after I essentially, to steal a phrase, lost my faith, so to speak. But I always liked it. I've never pushed back. I've always thought it was amazing. But yeah, you could almost bring it. You actually kind of have. It's probably a bit of an overship. If you want to bring a tear to my eye, astronomy documentary where I go through this, you look at it because it's just amazing. It's just looking at the planet. But as I said, I share a lot of those feelings with the people I've worked with. I have no problem what beliefs they have. A lot of the time, when we have a disagreement, I find it fascinating. It's a fun conversation to have. There's no hostility in it, and I think that's an important thing. Science is not out there to take anything away. It's there to give, not just in a sense about, like, say, medicine's an easy one to say, where you give you by improving people's lives directly, or engineering, the electrical understanding of it. I mean, lasers came out of a paper, Einstein paper in 1917. There was a theoretical one about it's known as stimulated emission, but it nearly 30, well, about 30, 17, but 43 years later it gave rise to the first laser, and now they're everywhere. But you also, I think, in this more sort of like awe-inspiring sense, it's very, very powerful. And yeah, these are the sorts of things that I love about it, and it's one of the ones that drives me to hoping I can stay doing science communication down the line much further. Is I want to share that feeling. This is But yeah, trying to explain it is I think sometimes our brains have a bit of trouble. But
Mm-hmm.
I think that's fine.
Mm-hmm.
We don't have to fully understand it. That's the science is a tool to help us explain it when our brains can't always comprehend it. Like maths with quantum mechanics, we can't. There is no intuitive understanding to quantum mechanics. That's just a sad reality of it. But that doesn't mean we can't appreciate it. It's yeah.
About how often should we expect additional pictures to be coming back?
That actually is a good question. For me, I really have to look into that one because, as I said, it'll be a constant stream. The life James Webb is expected to have a life of 10 years, at which
Okay.
point it will run out of fuel, and then it will they won't be able to realign it or do anything. It's been designed with some of the most efficient, some of the best fuel systems in mind. It's incredibly lightweight, so it's not as much to move, but eventually it will. They're hoping by that point they might be able to send robots out there to refuel it, and I hope they do. But who knows what other telescopes we've developed by then?
Mm-hmm.
So this is going to be an ongoing thing, and I think the more limiting factor is how long will it take us to start analyzing these images? Because it's one thing to look and for me to say this is these are the redshift galaxies, you've got the lensing, but also to be like, well, okay, what does that tell us? What do we know about that's going to take longer? That's going to take months on each image. People can spend their lifetime studying one aspect of astronomy, and that it'll take them sometimes it'll take years to analyze some of the information we're getting back. It was like the gravitational lensing paper. It was that I think that paper had it was one of the most longest list of contributors. Normally you might in physics, it's not uncommon to have maybe up to 8 people on a paper. This one had like 90 something. It
Oh,
was
wow.
just so many people that contributed to some of those first papers. Probably
Mm-hmm.
see a bit of that here, but it'll be a big collaboration effort and groups looking at very specific things. There'll be people will spend months studying one tiny dot in the picture behind me.
Mm-hmm.
Actually, that does bring me up something because before we go, because I know that one of the other images. Do you mind going back to that first one that came up when you went to the NASA one with all like the dust and the pillars? Because that's a bit different. I definitely want to mention that one before we go because this one I think is my favorite just because of what we're looking at rather than the actual imagery of it. But if we're talking in terms of the visual aspect of it, I'm trying to remember the name. That first image that came up, I'll recognize it is
Is
probably my
that it?
favorite.
Is that the one you meant?
No, sorry, the NASA link that I sent you. See if you can go to that. There was the panel of them. Let me see if I can. Maybe I can find it too. Come on, let me find this one. It's a very specific one. Here we go. I've got it. Let me just bring this out so I can. Do you mind if I share my screen again?
No, go ahead.
This one.
Oh, that
this
one.
image here.
Okay.
Yeah. Let me bring that up.
Mm-hmm.
So this one we're not looking quite as far back in time, but the columns here that you see. So I know it's a bit hard to see the mouse because some of these columns here are light years long. To give you a comparison, it'll take about 4 to 6 hours, depending on where Pluto is in its orbit, for light from our sun to reach Pluto. About 4 hours. These columns, that light can take 4 to 5 years to travel at. So we're talking millions of times bigger than our solar system for individual ones of these. And some of these brighter objects are closer stars, I believe. Some are supernovae. But what we're actually looking at in some of these is actually the birth of stars. This is a giant dust cloud.
Oh, okay.
And we're seeing stars forming in it. Eventually, this cloud will mostly disappear. You can actually see parts of it that are thinner than others. And if you look at like down the bottom left, you can see where I think a bit more of that dust has kind of been condensed into stars. But we are looking at stars being formed because this dust is slowly, because it's not perfectly even. There are parts that are a bit more dense. So over time, gravity pulls more and more to it. And as you get more can come in. And so eventually you'll get stars arising out of it.
Ted Franks asks, can we rename this God's Kitchen?
That's not a bad one. I like that name.
Or
A lot of them, in
God's
general, they're known
Nursery?
as stellar nurse. Oh, sorry.
God's Nursery, where stars are birthed?
Yeah, I think they're actually generally referred to as stellar nurseries. I think they have given this one a name. I'll have to double check it. I'll just stop sharing for the moment so I can see if I can find that name. Yeah, but every dot you could see in that image within the dust, most of them are new stars forming. Let me see if I can find most. Oh, and also here's another little interesting fact. The bluer images in that, the bluer items in that image are actually the hotter objects. And I'm just looking at some of the information again. One of the things that also helps is once they get hot enough, the UV radiation they give off will blast away the dust from around them. So that dust, as I said, will clear. And so they basically get born and then they manage to break free of the nursery. And some of these stars will end up with solar systems around them if they don't already. But it's just, you're basically looking at kind of the life-death cycle of stars, which is also pretty cool. We've seen a lot of that before, but we have not seen these parts of the universe in this detail. And there is another version of that image I'm having a bit more trouble finding, where you can actually see stars sort of, well, they've changed the wavelength and you can actually see through the dust. It's kind of this weird way to basically put a filter on that. Well, almost like X-ray vision, but in the infrared. There is also a lot of X-rays used in astronomy as well. There's so many images. There's actually one where you can see. If I may, I found actually here. This is another one. If I may be permitted to share my screen again. Sorry, I love these images. I could talk for hours. I think the hardest part you're going to have is probably shutting me up at the end. So this is from the ABC. So this is our ABC, the Australian Broadcasting Corporation. So it's basically Australia's equivalent of the BBC. Their one is brilliant because they actually go through and label them. But as you can see here, these are two stars. And they're basically one of them's cannibalizing the other one. So it's slowly eating the other star, as I believe. So it's the smaller one. So the bigger one is I'm trying to remember if the bigger one or the smaller one is the older one. But all of that dust around them is all the stuff they're throwing out. It's like all of the pushing away from them. And you'll find this is one of the James Webb images. And you can basically look at, it's almost like stars eating each other.
Interesting.
But they also got an image of galaxies colliding. I'll see if I can find that one too, because that one I found quite fascinating. So I'm just trying to jump between the various links I had. Here it is. Oh, yes. The name of this one they've got, Stephen's Quintet. They actually got an image that had 4 galaxies in it. And it's actually helped. So this goes back to an earlier question that someone had. The galaxy on the left, I think, is the closest one to it. I believe this one's a really distant one, but these two in there are actually colliding galaxies. So they're actually in the process of kind of running into each other. And you can see that kind of swirling process. And there is, I think, there's like 50, I think it's about 50 million light years off the top of my head between the distance of this one and these two. We're talking very huge distances. It's just this is a lot smaller and a lot closer, which is also why the details more there is they look more like a fainter dust. Yeah, I like that one. It is basically Star Wars, but so it's not just looking back in time, but we're looking at the universe in operation, in motion. We're seeing all of these things occur. So yeah, for is it Dog who asked the question? Who asked the question earlier about colliding galaxies? Because
I think that
I,
was
I,
Dog,
compl-
but I'm not sure.
I completely forgot. But yeah, James Webb's already got an image of that one. Yeah, that's the nebula. Also, this is what I was talking about. These two are the same image, but they're at different wavelengths, and you can see that the different wavelengths show you different things. So in this one here, I'd have to have a look. Or is these? Yeah, you can actually see where the difference in the image. One of them actually shows you the stars in there, whereas this one you can't quite see both of them because the dust shields it. So that's one of the benefits of using different wavelengths. But yeah, this one's actually a little closer. It's in the thousands of light years as opposed to millions or billions. But yeah, that's still these things. These galaxies, if they were looking at not galaxies, but these stars, if you're in orbit around them and you're looking back at Earth, you're looking at the rise of the Roman Empire when you look at the Earth.
Okay.
And if you're looking at, say, the Andromeda galaxy, your humans aren't around yet. I think that one's far enough away that you're actually probably. Wonder if the Earth's even
Dinosaurs?
formed by then. I have to check. I think to see dinosaurs, yeah, you would be outside the Milky Way to do that. So possibly. But yeah, you could actually, if you had a big enough telescope, this is what I like. If you had a big enough telescope, and let's say you had a warp drive to get to some of the ones that are, like, say, 50 million light years away, you could, well, I mean, not 50, but you'd have to probably go back. You have to go back 65 at least. You could go back and with a big enough telescope, watch the dinosaurs walk around. I don't know if it's physically possible to have a telescope that would do that, but just because of the way that
blows my mind.
Yeah, you can go back and see Earth's history. So some of the events that we're looking at, one of the when LIGO detected the black holes colliding, and later when they detected the two neutron stars colliding, those neutron stars collided back when New Zealand was still part of Australia, when it hadn't yet separated, and when dinosaurs still walked the Earth.
Wow.
And and the waves are hitting us now. And it's just a time scale, again, like what I've already mentioned, that is just so, like, I find it so hard to imagine. Like, I can appreciate it's big, but it's just, astronomy is so vast that it's so hard to just get into our head exactly what we're dealing with.
Yeah, yeah.
I'm going to stick to my lasers. They're much smaller.
Well, we are out of time. But I so appreciate you coming on here. I have learned a great deal. Some of it has been a bit over my head, but that's okay because there are other people that are in the chat and are watching this that have a lot more science understanding than I do. But I think I've learned a great deal from this discussion.
Well, hopefully I can be helpful. And yeah, I mean, I enjoy doing this. It was great. So thank you very much for having me on. Any opportunity to chat about this, I'm gonna jump at it.
Is there anything that you would like to shill for? Any other programs that you're going to be on in the near future?
I'm probably actually going to do another stream on this because obviously I said I can talk for so many hours with Jen that I'm planning to do Sunday morning. Apart from that, I said because of my work, I'm not going to shill anything else because it's going to be a little bit further down the line. I might do some specific scripted videos on this. I do want to do one on what scientists look like, but I have no dates on that. So the moment, just the one I'm doing with Jen on most likely Sunday morning Sydney time.
And while the question was up, I failed to say thank you to Eric. Eric, thank you very much for the super chat. I appreciate that very much. And what I have coming up, I don't have anything planned for next week's show. So next week's show will probably kind of a open mic night or community building night. And then I do have a show scheduled for the following week. And then after that, I am going to move back from Wednesday to Tuesday. There are too many other people who are big name that are streaming on Wednesday nights, and I'm just running into too many other shows. So I'm going to be moving back to Tuesday around toward the end of August. And this week, the produced video is going to be a combination of me doing a cooking demonstration on how to make macaroni and cheese while I discuss some of the historical fails of the Exodus story.
So a
And
unique combination.
yes, I tried it with creme brulee and Christmas, and it actually did not work very well. It was not well received, but I've been promising for some time to do a video on how I make mac and cheese. So I've got this one coming, and then I probably won't be doing any more cooking shows for a while because the cooking shows are not very popular. But that's okay. That's okay. I enjoy the anti-theism more anyway. So with that, I have to say good morning to Matt, as it is morning in Australia where Matt is, and good evening to my chat. Thank you everyone for joining us, and have a great evening. Live your life. Bye.